Okay, we'll get started. I've posted homework 3. Yay! It's available under week 6. It covers stuff. Let's see, what does it cover? Sampling importance, resampling. And then some basic MCMC stuff. Okay. So, you also have another midterm next week, one week from today, and I'm still writing that up. I haven't figured it out. I will probably use some of the kind of the mathy questions, problem 2 and problem 3 from the homework, as a basis for the midterm, and I'll try to probably work in also the Metropolis algorithm and possibly the Metropolis Hastings algorithm into the midterm as well. So I'll get a better picture of what the midterm looks like. But I think problem 2, I'll probably have something very similar straight up, which is in problem 2 here, I give you kind of like you create a 2x2 transition matrix for a 2-state Markov chain thing, and based on that, you have to create the stationary distribution or calculate that. And I think that's rather straightforward, but if you've never seen it before, or if you never practiced it, it could throw you off. So, practice that. And then problem 3 is very similar. It's actually straight from our textbook, and it's just kind of I'm having you create the 7x7 transition matrix. So in the textbook we had those 7 islands, and the politician is traveling to each of those 7 islands, and so you would have a 7x7 transition matrix. And so in problem 3, it's your job to create that using the actual values that you would use, and then you would see how multiplying a current kind of a distribution state by the transition matrix will change the resulting probabilities. And then if you keep multiplying by the transition matrix, it approaches that stationary distribution, and then you find the the stationary distribution, which are the eigenvectors of it's actually the transpose of the transition matrix. And so that's all part of the homework. And then the last bit for homework 3 is kind of running the Markov chain MCMC using the Metropolis algorithm for a single continuous random variable. And this is all meant to be kind of illustrative of the stuff we've been learning. And so I think in my opinion, it's not crazy hard, but perhaps I'm underestimating the assignment. So I think you guys can get started on it, and I think you guys can finish it rather quickly. I'll collect it. I have it due a week from Friday, so that gives you 9 days to work on it. And in my opinion, that's more than enough time for this assignment. But try it out. Again, well, I know that you got other classes, but I think if you get started on it, it's not too bad. Here. Okay. Are there any questions before I get started with lecture content for today? We're all good. How are we feeling about the Metropolis algorithm and MCMC stuff in general? Maybe like you feel like it kind of makes sense, but then you'll get a better idea when you try out the homework, maybe. Okay, yeah. So I recommend trying out the homework, and I'm hoping it's of learning value. Okay. Okay, and so today I will talk about the Metropolis Hastings algorithm. And so if you try to search for Metropolis algorithm, Wikipedia doesn't have an entry for the Metropolis algorithm. They only have one for the Metropolis Hastings algorithm, and they're very related. And so let me just kind of recap the Metropolis algorithm first, and then I will explain the difference between the Metropolis algorithm and the Metropolis Hastings algorithm. And there is, I didn't steal these, but because they're publicly available, but I created a link. I added a link to some lecture notes from the University of Illinois. And so anyway, when you that textbook that I've linked to, Doing Bayesian Data Analysis, that one only covers the Metropolis algorithm and then jumps to Gibbs sampling. Okay, and we'll cover the Gibbs sampler as well. If you look at the this textbook, the Introducing Monte Carlo Methods with R, they don't even cover the Metropolis algorithm. And so I think it's worth just talking a little bit about the Metropolis algorithm and how it slightly differs from the Metropolis Hastings algorithm. I think the Metropolis algorithm is just a little bit more intuitive, but we'll look at this. Okay, so the Metropolis algorithm. What? Maybe I should just ask, what's the big idea? Why are we bothering running the Metropolis algorithm in the first place? What are we hoping to get when we run this? That's a consequence. That's kind of why the Metropolis algorithm works, I should say, but that's not the actual goal of the Metropolis algorithm. So with the Metropolis algorithm, the hope is to get a random sample, or well, how is it? Yeah, it's to get a random sample from some target distribution, and the target distribution only needs to be known up to a multiplicative constant. Okay, and we said in Bayesian statistics this is a very common scenario where you might know the likelihood and the prior distribution, but you don't know the multiplicative constant that makes the PDF equal to 1. And we said that's okay. You don't need to know that. You just need to know it kind of just what it's proportional to. So the idea is, let me just write. The goal here is get a random sample to, approximate the distribution of, any PDF where we only know, or what's only required is where we only know the PDF up to a multiplicative constant. Multiplicative constant. Okay, so we might not know the exact PDF, and we're saying that's okay. We just have something that it's proportional to. Okay, so we had, f of x is, so we'll say the PDF is equal to, some constant times f of x, so that, the integral of the PDF is equal to 1, right? Okay, and the idea here is that we're just going to, with a big enough sample, we can get the approximate form of the target distribution. right? And then, if we have the approximate form of the target distribution, then we can start to answer questions about, its mean or its expected value and this and that, okay? So how can we get a random sample, okay? And the algorithm works like this, okay? So we start with some value, okay? And we'll just say this is our current value. I'll call it theta current. So we start with some value, theta current, okay? And then for the continuous case, we propose a new value, theta proposed, okay? Now, theta proposed comes from some distribution. And generally, we'll say the distribution is centered at, some distribution kind of centered or specified by the current theta value, okay? Specified by theta current, okay? This is called our jump distribution. And so a common choice for the Metropolis algorithm is, the normal distribution with mu equal to theta current. Okay? And we say, theta proposed comes from the normal distribution centered at theta current with some value sigma. So common choice is this. And this is actually a requirement of the Metropolis algorithm, is that this jump distribution be symmetric, okay? So I'll talk about that on the next slide, okay? So we propose a new value, theta proposed, and then we find the probability of moving. The probability of moving is going to be the minimum between 1 and basically f of the proposed value, so basically the value of the PDF up to a constant at the proposed location versus the value of the PDF up to a multiplicative constant at the current location. And we move with this probability. Okay? And that's basically it. Okay? So we figure out the probability of moving, and then we draw a random value between 0 and 1, and if it's smaller than that probability, we move, and if it's not, then we stay. And if we stay, we add another entry of theta current into kind of the random sample, so we get another entry at the current value of theta. Okay, so that's the Metropolis algorithm, and so the requirement for the Metropolis algorithm is that the jump distribution is symmetric. Okay, what does that mean? That means, okay, so this means that if we have the jump distribution of the theta proposed, the probability of getting theta proposed given theta current is equal to the probability of getting theta current given theta proposed. Okay, so the normal distribution works this way because let's say we have this. Yeah.
What is J?
J, this is the density of the jump distribution. Jump distribution being the value that we distribution that we use to propose values. Okay. Okay. This is the distribution used to propose new values, right? So in the kind of in the context, if we're using the normal distribution, our jump distribution, our jump function is our norm. Okay, our norm 1, we just need one proposed value, and then we give it the mean and the standard deviation. That's what our jump distribution is. So I guess the jump distribution is technically the PDF D norm. Okay, but effectively you know, when we use it to propose a value, we're using our norm. Okay, so we use, you know, for the code, as far as code goes, you know, we use our norm to propose a new value. Close the code. All right, and so what we have here is, if this is theta current, and over here this is theta proposed, we can say, you know, what is the density of getting theta proposed? Yeah, and we can also say, well, let's say okay, if we're centered at theta proposed, then what's the probability of getting theta current? Then we come up here, right? And so this height right here, this represents J theta proposed given theta current, and we find that it is equal to this location, which is J theta current given theta proposed. Okay, and that's what we mean by it being symmetric. So if we did, so you know, if theta current equals, you know, 10 and theta proposed equals 12 and sigma is equal to, I don't know, whatever, some number, 3, okay, then what we would see is that D norm of, let's see, 12, where given the mean is equal to 10 and standard deviation is equal to 3, this is equal to D norm 10, where the mean is equal to 12 and the standard deviation is equal to 3, right? This is what we mean by the jump distribution is symmetric. We're saying if the thing that we're given, because we start off with the current value to propose new values, right? And we're saying that with the jump distribution under the Metropolis algorithm, the proposed value, the probability of getting the proposed value based on the current value is the same as the probability of getting the current value based on the proposed value. Okay, so this is a requirement for the Metropolis algorithm. Okay, so this is So, the normal distribution, this works out nicely as a jump or proposal distribution for the Metropolis algorithm. The other algorithm that we were using for the island chains, what was the jump distribution or the proposal distribution there? It was a coin flip, right? And so it was saying, if I'm currently located at island 4, what's the probability I go to island 5? That's 0.5, okay, because I'd flip heads or tails. And then if I'm at island 5, what's the probability I propose island 4? Also 0.5, okay? So in that case, that satisfies the requirement in that the proposal, the probability of it being proposed, not the probability of it moving there, but the probability of being proposed is equal for going from 4 to 5 and going from 5 back to 4. So that worked out. Okay, we can relax this requirement. We can say, okay, I don't want to have to always deal with the normal distribution. Maybe I want to have a different proposal distribution, one that is not necessarily symmetric. Okay, when you do that, then you get the Metropolis Hastings algorithm. So the Metropolis Hastings algorithm this no longer requires that the proposal distribution or the jump distribution be symmetric. Okay, so we no longer J for theta proposed given theta current no longer has to equal theta current given theta proposed. All right, and so for example, you could have some distribution like this, where you're at 1, and then this is value 2. Okay, so if we start here, what's the probability of proposing this? Okay, this kind of jump is different from, let me just kind of reverse this now. Going that way, okay? So if we start here and then we're asking, what's the kind of the probability that we end up that way, it doesn't have to, the kind of the probability of proposing this value starting over here, it's not the same, okay? So kind of the probability of going from here to here is no longer the same the other way, okay? And so to accommodate this change, we change the acceptance criteria, okay? And so the probability of moving, so to allow for this change, okay, we simply modify the probability of moving. Okay, and so we say the probability of moving is still equal, it's going to be the minimum between 1 and this thing that we write out. The thing we write out is probability of theta proposed divided by the probability of theta current. Okay, so this part is the same, but then we multiply by kind of an adjustment. I just want to make sure I get this correct. Basically, we're going to kind of divide this by the jump distribution of going from theta proposed, getting theta proposed given theta current, times, and it's effectively theta current given theta proposed. Okay, so we take into account that when we proposed them, that maybe we were more likely to propose going to the right versus going to the left, or vice versa, and that gets taken into account here. Okay, so we're effectively kind of normalizing this by dividing this probability by this and dividing this one by that one. Okay, and so when you include this term, so this term accounts for a non-symmetric proposal or jump distribution. Right. If you use a symmetric jump distribution, then the top and the bottom are equal, and so this just cancels out to be 1. Okay, and then you get the good old-fashioned Metropolis algorithm. But if it's not symmetric, then you need to include this. And so if looking at the textbooks that we have, the Doing Bayesian Data Analysis textbook does not cover the Metropolis Hastings algorithm. This textbook on Monte Carlo methods just goes straight to the Metropolis Hastings algorithm and doesn't bother with the Metropolis algorithm to start with. So, does it make a huge difference? I don't know. And I think so. The Metropolis Hastings algorithm is probably the one that's this is the one that gets the entry on Wikipedia, and so it's good to know. But for me, when I was first learning it, this term kind of confused me in the beginning, and it's simply just a term to account for a non-symmetric proposal distribution. Yeah.
So I don't get why we want the jump distribution to be symmetric in the Metropolis algorithm, and why we need to adjust it to the Hastings algorithm.
Like why we want it to be symmetric? That's a good question. When it is symmetric and we use this, do we accept the move or not? As that is what makes what we call, in this case it's a transition kernel, because it's not a discrete case but it's a continuous case. That's what makes the transition kernel work in terms of getting us to the target distribution. I am not going to try to prove that the Metropolis algorithm converges to the target distribution. Maybe I can point you to some resources there. But yeah, when it's the Metropolis algorithm, using this proposed over current density, it only works and gets us to the target distribution if the jump distribution or proposal distribution is symmetric. And if it's not, then it's going to end up being biased towards well, you'll just not get the target distribution. So this accounts for that. Yeah. So if you're just going to use the normal distribution as the distribution to propose it, then this part will always equal 1, and so you can kind of just throw it away. Okay, and that's what the Metropolis algorithm is. When it's when the numerator and the denominator are equal to each other, then it's symmetric, and that's the Metropolis algorithm. Okay, so let me. I'll do a small demo here of maybe just the Metropolis algorithm to begin with. Okay, so we can start off with any kind of PDF that you want. Okay, so let's say I want to have something. Let's say the f of x that we want is, or the f that we want is going to be a function of x, and we'll just do negative x squared. Okay, so let's say we want to go for an upside down parabola. Okay, and we'll just go from, I don't know, negative 1.5 to 1.5. So we'll define our function. So just our arbitrary function is this. I don't know. We'll just do from -1 to 1. Okay, so from -1 to 1. So I think this is negative x squared plus 1. I think this is what I want. Okay, and so let me just kind of graph this. So x will just do a sequence from -1 to 1 by 0.001. Okay, and then we'll just plot x versus f of x. Okay, type equals L. Okay, so we'll say we want to try to get some PDF that's proportional to this. Okay, so this is our PDF up to this thing. Okay, so for MCMC, I just need to have some kind of arbitrary starting value that's wherever I am. So let's say kind of my current value will start at 0.5. Okay, and then I will have a proposed value. And the proposed value we'll use our norm centered at the current value, and I need to specify some kind of standard deviation. So maybe I'll just do 0.5. Okay, but we can change this. Okay, so this will be my proposed value, and now I want to know what is the probability of moving. So I'll just call this p move, and p move, well, let's do our ratio first. So our ratio is going to be f of the proposed value divided by f of the current value. Right? This is what we have. And if it were Metropolis Hastings, I would have to also multiply this by kind of our by this term, right? But right now, because my proposal algorithm or proposal distribution is the normal distribution, I don't have to worry about that. Is that okay? So I'm just proposing a random value, okay? And the probability of moving is going to be the minimum between 1 and the ratio that I have. Okay. There's an important thing here, and I have to modify my function f to say that if I propose a value outside of -1 and +1, then the associated probability there is 0. Okay, so I have to say that's going to be 0. So I'm going to just add some cases here, and I'll say if x is greater than 1, or x is, what do I do? Or x is less than -1, then return 0. Okay. And then we'll say else I guess I don't even need the else. It'll automatically do that. Okay. Otherwise, return that. Okay. So this will be my f. This is what I have. So I propose this. And then I move, and then I'm going to need a random value, runif1, and then we'll say if u is less than p move, then we move, right? Okay. So how do we do that? So if we move, then we update our current value with the proposed value, okay? Otherwise, the current value just remains. So we'll just do for I in 1 through, I don't know, 10,000, and we'll throw all of this in here. Is this okay? All right, and is everything in this code, does that kind of make sense? This is just the Metropolis algorithm. Okay, and so now I just need to kind of actually store the values. And so what I should do is we'll keep track of, I guess, results will be an empty vector, so I'll just repeat NA 10,000 times. And then, and then at the end of every iteration, I'll store my results and I'll put the current value in there, right? And so what this means is that if we don't move, then the current value goes in there anyway. And if we do move, the proposed value becomes the current value. And then we go in, and then the loop runs. All right, are we all satisfied with this? Okay, let's try this out. Let's see if, no, this didn't work. I don't know. Run. Is that running? Am I missing a closing parenthesis somewhere? I think I am. Huh? Oh yeah. Okay, that's why. There we go. All right, so let's throw that away, and then we'll escape out of here. Okay, so my f, that'll work. Okay, this works, this works, this works. Okay. All right, and we're done. And let's see if this works. Okay, so we'll create a histogram of our results. I really hope this worked. Okay, and I'm pretty sure it does. Okay, so and then we'll check this out. And look at that. It looks pretty good. So so that's it. That's the Metropolis algorithm. Okay, and if we want to check, we can do we can just plot all our results. Let's see. This is gonna type equals L. Okay, that's too much. Let's just do like the first 500 values. Okay, and so we can see how the algorithm just kind of bounces around the place, and effectively over the course of time, it's going to explore the entire distribution there. Okay. All right, so that's the Metropolis algorithm. Again, if you have a different proposal distribution, not the normal, but you have something that's not symmetric, you just have to change your ratio to include that kind of adjusting term there. Okay, we'll end here. We'll call it a day, and we'll see you guys on Friday.